Hello everybody and welcome back to another episode of Science with Mr. Emond. Today we're going to be continuing our unit on enthalpy. In the last video we went over a little bit of the theory of Hess's law and also looked at standard enthalpy of formations. And in this lesson we're going to be doing some calculations using that knowledge. Let's get started. Let's go ahead and try this example. So looking at this, it's kind of bare bones, isn't it? We don't really have very much here. But we have a process where we can use Hess's law. So let's go ahead and try that out. What do we know? We know that in order to form these products, we will have to have broken down these reactants. So let's start with that. CH4 is our first reactant. And how would CH4 break down? Well, it would break down into its standard states. What are the standard states of carbon? It's carbon, graphite, right? What's the standard state of hydrogen? Well, that would be hydrogen gas. And now to balance it, we need a 2 there. Okay. Let's do O2. So now we have 2 O2s. And they're going to have to break down. What's the standard state of oxygen? It happens to be oxygen gas, O2. So literally nothing happens here. This one has 0 heat of formation here, 0 heat of formation here. So delta HF for this one is 0 kilojoules per mole. Literally nothing happens. What's the delta HF for this one? Go ahead and look at your table of values. I'm going to look at mine. And I see that, well, I see a problem. How is my standard enthalpy of formation supposed to look? Well, this is supposed to be on this side, isn't it? Which means I'm going to have to remember that the sign has to get swapped. I'm going to leave it like this, but when I look at my table of values for methane, it says that the heat of formation for methane is negative 74.4 kilojoules per mole. However, that's when CH4 is the product. Right now, CH4 is the reactant, so it got swapped. So what do I have to do to the sign? Swap it. Don't forget that. That's a very dangerous step that a lot of students tend to forget. All right. Now let's think about, we have these products made by these things decomposing. How are we going to get CO2? Okay, how are we going to take these to make CO2? Well, I can say quite strongly that the carbon is going to be needed and the O2 is going to be needed, and this is likely going to form my CO2. What did I just write? This is the heat of formation equation, isn't it? Right? CO2 and its states, right? Its standard states. Do I have to balance anything? No, it's already balanced. So now I can look back at my table of values for the heat of formation of CO2 gas. And the heat of formation for CO2 gas is negative 393.5 kilojoules per mole. And again, you should have your table of values up so you can see it as well. You will need them when it's your turn. The fourth step, we need to make H2O now. How are we going to make H2O? Well, we're going to need hydrogen. What's the standard state of hydrogen? It's H2. Gas. We also need oxygen. What's the standard state of oxygen? It's O2, gas. Let's balance. 2 hydrogens, yep. We need 2 oxygens. We don't touch this one, do we? And so this, we need 1 oxygen, so this needs to be 1/2 O2. Okay? What is the delta HF for this one? Water as a liquid, it's negative 285 0.8 kilojoules per mole. Okay, now we're gonna have a little bit of a problem, aren't we? Because we've definitely, I'm gonna change my color here. We've definitely created our CO2 here, right? So we're good on this product, but how many moles of H2O do I need? I actually need 2 of them. So what am I gonna have to do to this equation? I'm gonna have to multiply by 2. And so here's where, again, like you're gonna have to remember these little steps here. I'm gonna have to multiply this by 2. So let's create our 5 here, which is 2 H2s plus 2 times 1/2 is just 1. So now we just have O2 gas goes into 2 H2Os as a liquid. And our delta HF for this one is now this multiplied by 2, which is negative 571.6 kilojoules per mole. Okay, I'm gonna go ahead and maybe, what am I gonna do? I'm gonna make a line, quite a thick line, and I'm gonna cancel this step out because it's gone, right? We've made step 5 out of step 4. So this is the one we're gonna use. Okay, let's go ahead and now figure this out. What does Hess's law state? It states that the delta H, let's not show that yet, shows that the delta H of the reaction is going to be equal to the sum of all the steps. So what are my steps? I had this step, which was positive 74.4 kilojoules per mole. I had 0 kilojoules per mole. I had negative 393.5 kilojoules per mole. And I had negative 571.6 kilojoules per mole. Now, when I add that all up, I end up with a delta H of my reaction of, let's take out our calculator because I need help on this one, 74.4 minus 393.5 minus 576.6. No, 571.6 equals 890.7 kilojoules per mole. We're just going to double check things now. CH4, is it anywhere on the right-hand side? No. Carbon, is it anywhere on the left-hand side? Yeah. That's gone. We have 2 H2s here. Is it gone on the right-hand side? Yeah, it's gone there. We have 2 O2s here and 2 O2s there, so that's just gone. We have 1 O2 here and 1 O2 here. Is there any O2s on the right? No. Now, I think we're kind of done, aren't we? Because these can't get canceled out either. So let's see what we're left with and watch what happened. We're left with CH4 on the left. There it is. Maybe I'm going to switch to a highlighter. There's my CH4. Okay. I'm left with 1 O2 there and 1 O2 there. That's 2 O2s. There it is. I'm left with a CO2 on the right. There it is. And I'm left with 2 H2Os on the right. And there it is. So that's why I can add up all these steps, because these steps were required in order to get back to my original equation. When I add them all together, I get my delta H of the reaction, 890.7 kilojoules per mole. Now you might be saying to yourself, Mr. Emond, there must be a better way. Yep, there is. And that's why this is down here. So, the following equation, this one, and a delta HF table of values, and Hess's law can be used in conjunction to solve for the delta H of a reaction. And here's the beautiful reaction that will save your life. The delta H of a reaction is going to be equal to, this says, the sum of however many moles of each product you have times the change in enthalpy of formation for that product. And each product needs to be added together because it's the sum, minus the sum of the same thing for your reactants. Let's see how this looks for this one first. So see how much easier it could have been. Look at your standard enthalpy of formations. Pull it up and follow along. I need the sum of my number of moles of my products times their delta HF value. So I have two H2Os. So I'm going to go 2 times, what's my standard enthalpy of formation of H2O as a liquid? It's negative 285.8 kilojoules per mole. Excellent. And I need to do my other one. What was my other product? CO2. How many moles of CO2 do I have? Just 1. What's the delta HF for that one? For CO2, it's negative 393.5. 393.5. Again, kilojoules per mole. All right. That is this. I've done the sum of my moles times the HFs for each of my products. Now I need to subtract the sums of my reactants. So what are my reactants? CH4 and O2. How many CH4s? Just 1. 1 CH4, what's the delta HF for CH4? Negative 74.4 kilojoules per mole. And then I have 2 O2s, and O2s have a standard heat of formation of 0 kilojoules per mole. Okay, now you just solve. Let's take out our calculator. Two times negative 285.8 plus, well, I don't know why I did that, because it's just multiplying by 1, negative 393.5. Okay. Minus, there's only one value here, and it's negative 74.4 equals. How interesting that this would equal negative 890.7 kilojoules per mole when that is what we found. So obviously this is way easier, don't you agree? Please agree. It's way nicer. So let's try this for something that we don't need to do that long process for. Let's just use this formula. Okay, so we're gonna be looking at our standard heat of formations again. Delta H of the reaction is going to be equal to, we have 1 aluminum oxide, and aluminum oxide, I'm looking for it on my paper, has a standard heat of formation of negative 1675.7 kilojoules per mole. And our other product, we have 2 of, and it's iron, which is in its standard state. Okay, minus our reactants. And we have 2 aluminums, And aluminum's in its standard state, so this is 0. And we have 1 iron oxide, and iron oxide's not a standard state, it's made of different things. Iron oxide is negative 824.2 kilojoules per mole. All right, throw it in your calculator. So now we have 1 times negative, so I'm just going to type in negative 1675.7. That next part is 0. And then we're going to be subtracting negative 824.2. And this gives me a delta H of my reaction of negative 851.5 kilojoules per mole. And that's it. Okay, it's going to be your turn. You're going to need to use your heat of formation table of values. You're going to need Hess's law, and you're going to want to use this equation here. And do that for these 2 problems. Now, I'm going to give you a little bit of a hint because I don't want you wasting your time. Look at those problems. Are they balanced? Once you're done and you have the solution, you can come on back. Till then, pause the video and work them out. See you soon. Okay, welcome back. I hope my hint panned out for you. Let's take a look at the solutions. So, the first thing that you should have done is balance them. And so you would have made the first equation with the leading coefficients 1, 3, 2, and 3. That's important, okay? Because when you set them up in here, you're going to need those values here. So we have CO2 first. There's 2 moles of CO2, and here's the standard heat of formation. 3 moles of H2O, and there's the standard heat of formation. 1 mole of, that's ethanol, and there's the standard heat of formation, and 3 moles of water, and there's the standard heat of formation. You add them all together, and you get the change in enthalpy of the reaction to be equal to negative 1409.2 kilojoules per mole. In the second reaction, you would have found the leading coefficients to be 6, 3, 1, and 7. And those are going to be used in your problem. So first, there's 1 mole of phenol. There's 7 moles of oxygen. There's 6 moles of CO2 and 3 moles of H2O. Add them all together, and you get your delta H, standard enthalpy of the reaction is 3053.4 kilojoules per mole. That's it for this lesson. Thanks for watching, everybody. You can like, follow, and subscribe to my social medias to get notifications as soon as new content is uploaded. In the top corner here, you will find the playlist that this video is in. Watch the unit from beginning to end, and over here, you will find the next video in this unit. Keep learning, everybody. Take care.